Let us do another problem, max cut, okay, which has a similar flavor. My input is a graph, undirected graph. Output is a partition of the vertex set. Such that number of edges going across is maximized. Now, so is the problem clear? I have to draw at least one graph in each lecture. So, if I pick 1, 2, 3, 4 in one part and 5, 6, 7 in another part, how many edges are across the cut? 3 edges are going across the cut, right? 3 edges are going between the two parts. I do not know whether this is a max cut. You can maybe come up with different partition where you will have more edges crossing the cut. You can also ask the minimization question here. You want a partition of the vertices such that minimum number of edges cross the cut. Okay, how? Because okay, first of all, max flow requires an S and T, and it actually gives you a min ST cut, but still you are there. You can add S and T, a dummy S and T, or use one of your vertices as S. Let us say I fix one vertex as S, okay, and fix one vertex as T, and yeah, so what, right. So, he says there are n square combinations. Actually, you do not have to do n square combinations, fix S and vary T, that alone is enough, because what max flow gives you is a min ST cut. If you fix an S and fix a T, then a partition where S is here, T is here, so that, and among such partitions minimum number of edges, min cut is what max flow will find you. So, you fix some S and vary your T, then you will get n many max flow computations will give you the min cut. So, min cut is poly time solvable, but max cut is NP hard. Okay. So, min cut in fact, next week you will see some interesting randomized algorithm to compute min cut even faster than doing flow. Okay. But max cut we will not do it here, but it turns out max cut is NP hard. So, it is another maximization problem. So, what is the output we are looking for? What is the output? That is why I always write it down. So, you do not, the output is this. You want a partition. Output is a partition among all such partitions. So, it is very important to be clear about what is your input, what is the output. Okay. I want a partition among all such partitions, that partition which maximizes the number of edges across. Okay. Can somebody give me a randomized algorithm? The way we did it for SAT. Maybe somebody else. So, what did we do for max SAT? We said oh, what are you looking for? An assignment. I will give you a random assignment. That was a randomized algorithm, right? Pick what do you want for every variable. You want 0 or 1. I will toss a coin and decide. What do we want here? We want a partition. So, randomly pick what? Okay. So, what is the exact experiment you do? For each vertex, I toss a coin. If it comes head, I will put it in S. If it comes tail, I will put it in S bar. Right? You want a partition. So, let us fix these two sets, and I will decide who goes here randomly. Right? So, here is a randomized for x in V, place it in X, with probability half, and in S bar, okay, so it is a random experiment. I got a random partition, trivial linear time algorithm. Now, what do I want to analyze? Because what is my objective value? Number of edges going across the cut, right? Now, since it is a random experiment, I can only do an expected number of edges going across the cut. Okay? Expected number of edges going across the cut. I can do exactly the way we argued before. So, what did we do here? I said this is our first set. You want to maximize the number of clauses satisfied. So, I go to a clause and ask what is the probability that this is satisfied. We argued here. What is it you want to maximize here? Number of edges crossing the cut. So, you go to an edge and ask what is the probability that this edge is between S and S bar. Okay. I do not want answers quickly, just want somebody else to answer. So, slow. And an edge is crossing the cut if this happens. One of the two happens, right. If I look at the endpoint, this must be in S and this must be in S bar, or this is in S bar, this is in S. So, what is the probability of that happening? Let us pick an edge x y. I want x to be in S, y is in S bar. What is the probability of that happening? What is the probability that x is in S? 1 by 2, because that is how I chose. What is the probability that y is in S bar? 1 by 2. What is the probability that both simultaneously happen? 1 by 4. And then I have the other probability of this happening, that is 1 by 4. So, you will add both of this, because these are exclusive events. And so, probability that x y in E, okay, let us say x y is in E, then probability that x y is in cut. So, I am going to say so, expected number of edges in the cut S S bar number of edges by 2. Linearity of expectation, exactly the way we did it. Expected value that Ci equal to 1, run it over all edges, and each one of this is half. So, this is a half approximation algorithm, right, because the solution produced is at least half times the opt, because opt can be at most m, because you want to maximize the number of edges crossing the cut. Maybe it is a bipartite graph, all edges will be crossing the cut. And can be de-randomized as before. Because the way to think about it is, what is this saying? That there are sort of 2 power n ways of partitioning my vertex set, right, because once I choose S, S bar is fixed. Out of all these partitions, for each one I count the number of edges crossing the cut and add and take the average, and that is what is m by 2. So, there must be one partition which gives you at least m by 2, and the way to find it is just put one S in S, one vertex in S, and do a random partitioning on the remaining, compute the expectation, put S in x in S bar, put the remaining, compute the expectation, whichever is larger, that will help you decide whether you should put x in S or S bar. And repeat this in polynomial time, you will actually get a partition which has a good number of edges crossing the cut. Okay, this is a, I will leave this as an exercise, but I more or less said how to do this. Okay, so here are a couple of maximization problems, maxat, maxcut. Again, here also the ratio can be improved using linear programming techniques. Again, linear programming and even more extended version called semi-definite programming, which is picked up in the last 10 years, using which these approximation ratio has been improved from half to 0.878 or something. Okay, you can bring it close to 1. So, you can find a cut which has a large number of edges compared to the optimum. Okay, so hopefully you got a flavor of approximation algorithms, where you want to optimize some objective function. These problems are hard, and you want some algorithm, some heuristic kind of thing, but the important challenge is to look at the solution produced for an arbitrary instance and compare it with the size of the optimum solution, and make this ratio, approximation ratio, close to 1 as possible. Okay. There are problems for which we have seen half, 1, 1.5, 2, log n, and I also said there are problems which can be where the approximation ratio can be as close to 1 as possible at the cost of increased running time. Okay, so the next topic, so we will move on from approximation. We have seen NP hardness, we have seen approximation, and we want to deal with NP hard problems. Now, I am going back to exact algorithms. Nothing approximate about it, but these will be exponential algorithms. Here the goal is to improve the base of the exponent. Okay, in the world of exponential algorithms or exponential functions, there is n factorial, 2 power n, 1.3 power n, and we want to just improve the base. Okay. Yeah. So, let us look at again the 3 SAT problem. m clauses, n variables. So, what would be a brute force algorithm to, what would be an exponential algorithm to test satisfiability? How much time? 2 power n, right? 2 power n, and for each time you check for size of the formula, I am going to say, run through the formula and check whether your assignment is satisfied. Now, I want to improve this base. Can I improve it from 2 power n is the question, right? Clearly, there are certain assignments you do not want to try, right. So, suppose your C1 is x1 bar or x2 or x3 bar, okay, and you have other clauses. Some assignment you do not even want to bother checking. Which assignment? So, an assignment which sets x1 to 1, x2 to 0 and x3 to 1, why even run through and check? You do not have to spend your whole linear time to check that it is not satisfiable, but you can just avoid doing these assignments. Okay. So, basically I look at C1, let us say, and say, oh, there is one assignment which will not satisfy this. So, I will not set for those variables, I will not set that particular assignment, and I am going to try the remaining. Okay. Just some simple improvement by just looking at C1 alone. So, how much would you save? How many assignments you are not checking? 2 power n minus 3, right, exactly. So, what is this, that x1, x2, xn, there are 2 power n assignments, and what he is saying is x1 equal to 1, x2 equal to 0 and x3 equal to 1, and I do not care what these variables are, do not bother checking. So, I save so much. How many such assignments, how many of the 2 power n assignments has x1 equal to 1, x2 equal to 0 and x3 equal to 1? 2 power n minus 3, because these 3 variables are fixed and the remaining variables are free. So, 2 power n minus 3 assignments you are not checking. Okay. So, that is your saving. So, this gives you 2 power n minus 3 is what? 1 by 8 times 2 power n, right. So, this is like a 7 by 8 times 2 power n number of assignments you are checking. It is not really an asymptotic improvement, okay, some improvement, but it is not your overall f of n does not improve. But turns out there is a way to actually use this simple idea and improve it asymptotically. Let us see how, right. Basically apply this whole idea recursively. Okay. So, if you think about the recursive algorithm, your 2 power n algorithm, which starts with x1 equal to 0, or let us pick the 3 variables x1, x2, x3, right. Totally how many choices are there for x1, x2, x3 in general? 8 choices, and you are trying only 7 choices now, right, because you know that one choice is not worth checking at all, you know it trivially. Now, if I recurse, what happens? Let us see, right. So, what is my recursive algorithm for testing satisfiability? Go to my first clause, pick the 3 variables and try the 7 possibilities for those 3 variables. At the end of it, how many variables you have removed? 3 variables. In each of the choices, you have set these 3 variables. So, these 3 variables go away from your formula. Now, we have a new formula. So, here is my algorithm, right. For each of the 7 assignments, recursively check whether the remaining formula is satisfiable. The good thing is, in remaining formula I have gotten rid of 3 variables. So, what would be the recurrence relation for this algorithm? I am solving 7 problems of smaller size. T of n equal to plus some polynomial time. Okay, don't bother about it. What does this solve to? Don't have a master theorem to try this, but you can just expand it out and solve it. So, in this world of, so these are called branching algorithms. Basically, it is like a backtracking or whatever you would have seen it. We are trying brute force all assignments, but we know that certain assignments early on we rule out quickly, and that helps your recursion. So, can we try and expand this? So, suppose I do not have the 7 times t of n minus 3. This would be 7 times t of n minus 6. Finally, I hit when there are like 1 variable, 2 variable, and quickly solve them. How many 7s will I have? N by 3, right? Because each time n goes down by a factor of 3. So, 7 power n by 3. How does it compare with 2 power n? 2 power n is what power n by 3? Eight power 1 by 3 is 2, right? So, 8 power n by 3 is 2 power n, and I managed to get 7 power n by 3. So, this is actually 7 power 1 by 3 whole power n. So, this is strictly less than 2, because 8 power 1 by 3 is 2. Okay. So, now I got an asymptotic improvement to this algorithm. It is no longer a 2 power n, this is some 1 point, I do not know, anybody knows what 7 power 1 by 3 is? My guess would be something. Now, we did not do anything clever at all. We just picked one clause and said, instead of doing an 8-way branch, do a 7-way branch. I mean, another way to think about it very easily is that you are doing a 7-way branch and getting rid of 3 variables. The next level, it will be another 7-way branch, and some 3 variables will go away, and the height of this would be like n by 3. So, 7 power n by 3. Okay. But the key thing is that we now actually have an exponential improvement. It is not 7 by 8 power 2 power n, it is some small base power n. Okay. Let us do one more example and then I will stop. So, is the idea clear? Goal is to get exponent. I mean, next lecture I will give you actually even completely using dynamic programming techniques, we can get some very nice improvement for certain problems. Here it is a simple branching algorithm. Okay. This is a very powerful technique, but you would have seen it, you might even be implementing using backtracking, but here we can formally analyze and argue that the running time is asymptotic improvement over our simple 2 power n. So, let us do minimum vertex cover, right. We have seen this problem several times and you are going to see it again and again next week. What are we looking for? We are looking for a subset of vertices that cover all edges. A brute force algorithm will be to try all possible subsets. There are 2 power n subsets, that is like a 2 power n algorithm. Okay. But clearly again there are certain subsets not worth trying, which is an idea which you can use to improve the base of the exponent. So, or here is another little idea. Suppose let us pick a vertex x. Let us remove isolated vertices from the graph, they are not playing any role to cover edges. Okay, let us assume that there are no isolated vertices. We have seen this, if x is not in the solution, solution is what I am looking for, then what can you say? I am trying to cover all edges, then what? What did you say? The neighbor of x. All the neighbors of x must be in your solution. It is a very powerful statement, very useful statement, right. So, if x is not, so you are trying all possible subsets. In one subset you pick x, in the other subset you do not pick x, no point in trying some 2 neighbors of it. You know that all neighbors, why? Because if x is not in the solution, who will cover this edge? This vertex. Who is going to cover this edge? This vertex. So, all neighbors of x okay. Now, this gives you a starting point on a branching algorithm. So, algorithm let me write it pretty informally, delete x, x is some vertex not isolated, check if g I mean find the minimum vertex cover of, okay. Why do not I write this a one line algorithm, minimum vertex cover of g, sort of like the dynamic program kind of thing in branching, is equal to, so x is some vertex, but not isolated, 1 plus minimum vertex cover of g minus x, or degree of x plus minimum vertex cover of g minus neighborhood of x. I have to write some more thing to complete it. What do I have to do? These are 2 quantities, minimum of the 2. Just pick some arbitrary vertex and say, okay, minimum vertex cover may contain this. So, I take this, if it contains, it covers all the edges incident on that vertex. So, delete that vertex, go to the remaining graph and pick the minimum vertex cover, add this number. This is one possible vertex cover. If x is not in the solution, then I know that all its neighbors are there. So, include all the vertices and then delete them all, because they cover whatever edges covered by their incident on those vertices, and find the minimum vertex cover on the remaining graph, pick the minimum of the 2. Okay. So, now if I implement this as a branching algorithm, let us see how it will happen, right. It is a recursive algorithm, you can write a recursive algorithm the way we wrote for SAT, so pick any x, delete it, recursively check whether find the minimum vertex cover in g minus x, it gives you some number. In the other branch, take all the neighbors, recursively check whether find the minimum vertex cover of the remaining graph, right. So, my branching algorithm would be, and it starts here and I say here I will have g minus x, in this branch g minus n of x. So, 2 sub problems of smaller size, right. But what can you say about the sizes of these? If n is the number of vertices in the original graph, what can you say about the sizes of these 2 sub problems? So, how many here? N minus 1, because one vertex is gone, n minus 1. What can you say here? Yeah, but degree of x can be 1, 2 in the worst case, right, because all I just said is no isolated vertices. So, x's neighbor would have gone. So, this could also be n minus 1. X would also be gone. Okay. Why? Because I am just deleting only the edges incident on x. If it is of degree 1. Okay. So, yeah, I think both have same idea. So, what is being said is that suppose I am very unlucky, I mean ideal thing would be I pick a very high degree vertex and do this branching, then this will be n minus 1, this will be n minus the degree of the vertex, and if the degree of vertex is very large, great, I will have a good branching. Okay. I have to write a recurrence relation and see what it is, but at least we see that that should be good. But if x is of degree exactly 1, then this will be n minus 1, this will be also be n minus 1, but the observation is that if x is of degree 1, y may have a lot of things, then when I delete neighborhood of x, which is y, this vertex is gone, but x will become isolated. If you are removing isolated vertices, this will also go. Okay. So, at least 2 vertices will be gone. I mean, there are lots of different ways to carefully analyze this. So, then what would be my recurrence relation? T of n would be 2 subproblems. What is recursive subproblem? T of plus T of n minus 2, because we just argued. See, if this is also n minus 1, then I am not improving, because this will become 2 power n. It is 2 times T of n minus 1 back to 2 power n, which is what I am trying to improve. But now I argued that n minus the 2 vertices would be gone. So, T of n minus 2, what is the solution to this? Does this look familiar? Recurrence, Fibonacci recurrence, what is the solution? Golden ratio, what is golden ratio? Yeah, 1 plus square root of 5 by 2. Okay. So, that is like 1.618. So, this solves to 1.618 power n, big improvement from 2 power n, and we have not done anything, right. If you go inside and carefully, so here are some trivial improvements. Suppose, I mean, one idea is you pick the high degree vertex and branch, right. But if the high degree itself is 1, what does that mean? No, if the graph has high degree 1, what does that mean? You can't even have a path will have degree 2, right. So, it will be like isolated, it basically edges, it is like a matching and some isolated vertices. The maximum degree of the graph is 1, you will not even get to this algorithm. First find that, you will solve it in polynomial time, right. Minimum vertex cover in such a special graph, you can solve it in polynomial time. Suppose maximum degree in the graph is 2, what does that mean? How does the graph look like? Maximum degree is 2 is like paths and cycles. That is also a very special graph. You can solve it in polynomial time. So, you might first check the maximum degree, if it is 1 or 2, you do not even come here, right. The maximum degree is 3, you can't solve in polynomial time, because cubic vertex cover is also NP hard. But then you pick a vertex whose degree would be at least 3 here. So, 1 will go away and at least 3 will go away here. So, you actually get a better base here, not 1.6, but you can even improve it. Okay. So, this is sort of the game in this idea of exact exponential algorithms. There is actually a whole nice small book on exact exponential algorithm, which has recently come out in the last 4 or 5 years, where no approximation, problems are hard, you want to solve them exactly, you have to live with the fact that you have exponential time algorithms only possible, but improve the base of the exponent. So, you can deal with larger and larger sizes of n in reasonable time, and we will see more examples in the next lecture.